Welcome, data architects and AI engineers. Today, we are exploring Snowflake Cortex Search. I will be your senior trainer, guiding you through implementing high-performance hybrid retrieval to power your retrieval augmented generation, RG, applications directly within the AI data cloud. Let's get started. Let's begin by defining Cortex Search. In the era of generative AI, passing raw, unstructured data to a large language model is not enough. You need precision. Cortex Search is a fully managed service that enables low-latency, high-quality semantic search over your Snowflake data. What makes it so powerful is the automation. It gets you up and running with a hybrid search engine in minutes, completely removing the burden of manual infrastructure maintenance, search quality tuning, or ongoing index refreshes. Why do we use it? The two primary enterprise use cases are Retrieval Augmented Generation, or RAG, for chatbots, and high-performance enterprise search. By retrieving the most contextually relevant chunks of data and supplying them to an LLM, you ensure your AI applications are grounded in your proprietary truth. And it is incredibly simple to implement, requiring just a single SQL command to initiate the indexing process. Let's look at the high-level architecture in this flowchart. On the left, your application or user submits a search query. This request hits the Cortex Search service. Notice the connection to your Snowflake tables. Cortex Search handles the automatic indexing of your data in the background, ensuring your search surface is always up to date without manual pipelines. It returns low-latency, relevant text chunks to the application. In a RAG architecture, your app then takes those highly relevant search results and passes them as context to a Cortex LLM, which finally delivers a precise, grounded answer back to the user. To understand why Cortex Search provides such excellent results, we must look under the hood at its hybrid engine. Cortex Search does not rely on just one search methodology. First, it utilizes vector search, converting your text into dense embeddings to retrieve documents that are semantically similar, meaning it understands the underlying concept, even if exact words differ. Simultaneously, it performs keyword search, retrieving documents based on lexical similarity to ensure exact names, IDs, or distinct terminology aren't missed. But it doesn't stop there. Cortex Search applies semantic re-ranking. It takes the merged results from the vector and keyword searches and uses an advanced re-ranking model to reorder the documents, guaranteeing the most contextually relevant results bubble to the top. This multi-layered hybrid approach achieves state-of-the-art search quality across a broad range of datasets without requiring you to manually tune complex algorithms. This diagram perfectly illustrates the internal data flow of a Cortex Search query. When the user search query enters the system, it forks into two parallel execution paths. On the left, the vector search engine hunts for semantic meaning. On the right, the keyword search engine hunts for exact lexical matches. These disparate result sets are pushed into the result merger. Instead of just returning these to the user, the merged list passes through the semantic re-ranker, which evaluates the exact context of the prompt against the retrieved texts, outputting the final top K highly relevant results to your application. Deploying this architecture is handled entirely via native Snowflake objects. To create a service, you execute the Create Cortex Search Service SQL command. You define the on parameter, which specifies the exact text column you want to index for searching. A critical configuration is the target lag parameter. This tells Snowflake how frequently to check the base table for new or updated rows, for instance. Setting it to 1 hour ensures your search index is never more than an hour stale. You also define attributes. By listing columns like region or category here, Cortex Search will index them alongside the text, allowing your application to retrieve them or use them for strict filtering. Finally, you must assign a virtual warehouse to the service. This warehouse is used exclusively to materialize the results and compute the ongoing index refreshes. We highly recommend dedicating a warehouse of size medium or smaller to effectively manage these background costs. Here we see the structural components involved in creating the service. Your source table data is pulled in via the AS subquery in your creation statement. The Create Cortex Search Service engine splits this data functionally. The column specified in the on clause goes into the heavy vector and text index, while the columns listed in attributes go into the lightweight filter index. Notice the dedicated warehouse at the bottom. It acts as the motor, automatically spinning up to power the data refreshes according to your defined target lag schedule. To optimize your RAG pipelines, you must understand embedding models and tokenization. When you create a Cortex Search service, you select an embedding model. Snowflake provides several out-of-the-box, such as Snowflake, Arctic, Embed, v1.5, which is highly optimized for English or Voyage multilingual. 2 for global datasets. Every model has a fixed context window A maximum number of tokens it can embed at once, often 512 tokens. If a row contains text longer than this, Cortex Search will automatically truncate it before embedding. To prevent data loss and ensure maximum RAG accuracy, the best practice is to proactively chunk your large, unstructured documents into overlapping segments of about 512 tokens before feeding them into the search service. By providing smaller, highly focused chunks, the LLM receives much cleaner context. Lastly, remember that you incur compute costs for embedding these tokens every time a new row is inserted or updated. This flow demonstrates the ideal ingestion pipeline for large documents. A raw unstructured document, like a massive PDF, should not be ingested directly. Instead, it passes through a Snowflake text splitter function to create smaller, logical chunks, ideally around 512 tokens each. These chunks are independently passed into the Arctic embed model. The model translates the semantic meaning of each chunk into dense mathematical vectors stored in the Cortex vector index. Because this step requires GPU-level compute, each embedding operation inherently links to your billing metrics. Once your index is built, how do your applications retrieve data? Cortex Search provides high-performance endpoints via the REST API and the Snowflake Python API, as well as a search preview SQL function for quick testing. A query payload is simple. You provide the natural language query string, an array of the columns you want returned, and a limit for the number of results. The true power for enterprise apps lies in the filter object. Because you defined attributes during creation, you can push down highly optimized JSON filters using operators like @EQ for exact matches, @contains for arrays, and logical @and/or @or operators. Security is critical here, while the service executes using owner's rights to ensure fast retrieval. You should inject context-aware filters such as passing the current user's email into an @contains filter to ensure they only retrieve documents they are authorized to see. Let's trace a secure application query in this sequence diagram. The app issues a POST request to the Cortex Search API, passing the user's natural language query and a strict attribute filter, such as limiting the search to a specific region. The API first hits the index to apply the attribute filter, immediately narrowing down the filtered candidate set. Only then does the heavy hybrid search and re-ranking execute on the authorized subset. Finally, the top K results are returned as a clean JSON response containing both the text chunks and their associated metadata. For advanced use cases, Cortex Search supports multi-index configurations. Instead of searching a single column, a multi-index service evaluates multiple columns across different modalities simultaneously. For example, in an e-commerce platform, you want to use text indexes for columns like product SKUs or category names where users expect exact lexical matches. Conversely, you use vector indexes for long-form columns like product descriptions where users search by semantic intent. Cortex Search blends these automatically. Furthermore, if your data science team has already generated highly specialized vector embeddings outside of Snowflake using a custom model, Cortex Search fully supports user-provided embeddings. You can upload these pre-computed vectors and combine them with native text indexes, giving you the absolute ultimate flexibility to design a bespoke hybrid search architecture tailored uniquely to your enterprise data. This class diagram maps out the versatility of a multi-index search service. The core service object aggregates multiple indexing strategies. It utilizes text indexes strictly for fields requiring a lexical focus, like SKUs or brand names. It simultaneously leverages vector indexes for fields demanding semantic focus, like descriptions. It can even incorporate user embeddings for custom vectors brought in from outside models. When a user submits a query, the engine intelligently interrogates all these linked indexes simultaneously to synthesize the perfect response. Let's tie this all together with a highly valuable real-time use case, an enterprise RAG chatbot for customer support. Imagine your telecommunications company wants a chatbot that helps technicians troubleshoot internet connectivity using historical support transcripts. Step 1. We ingest the transcripts into a Snowflake table and execute a Create Cortex Search Service command, indexing the transcript text and setting region as an attribute. Step 2. A technician opens a Streamlit app and asks, "How do I fix a router offline error?" The Python backend intercepts this, queries the Cortex Search service via API, and applies a strict filter to only search transcripts from the technician's specific region. Step 3. The service instantly returns the top 3 most relevant historical fixes. The app injects these exact texts into a prompt and passes it to the Cortex AI complete function. The LLM reads the context, synthesizes the steps, and returns a grounded, factual answer. Hallucinations are eliminated. Follow the sequence diagram for our RG chatbot. The support tech asks a question in the Streamlit app. The app acts as the orchestrator, first requesting context from Cortex Search with a specific regional filter. Cortex Search returns the top historical transcripts. The app then packages the user's question and these transcripts into a single, context-rich prompt. It sends this payload to the AI Complete LLM service. Because the LLM is restricted to the provided context, it generates a highly factual resolution, which the app displays to the tech fast, secure, and accurate. Finally, we must architect for cost management and observability. Operating a Cortex Search service incurs 3 primary cost vectors. First is warehouse compute. The virtual warehouse attached to your service consumes standard credits when it spins up to refresh the index based on your target lag schedule. Second are embedding costs. Whenever new rows are inserted or updated, the system automatically calls an embed text function, charging you a fractional compute cost per token processed. Third is storage. Snowflake charges a highly predictable rate of 6.3 credits per gigabyte per month for the data persisted inside the search index. You can monitor all of this transparently using the Cortex Search Daily Usage History Administrative View to ensure your RAG pipelines remain economically viable. I hope this deep dive into Cortex Search has empowered you to build incredible AI applications. I invite all learners to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final diagram breaks down the total cost of ownership for Cortex Search. Your costs are divided into warehouse compute driven by your refresh schedule, embedding token compute driven by the ingestion of new or updated rows, and index storage costs scaling with your data volume at 6.3 credits per GB per month. To maintain strict financial governance, all of these vectors feed telemetry directly into the Cortex Search Daily Usage History View, giving your FinOps teams complete visibility and control over your AI infrastructure.